Awesome.
Here we go. Let's look at reflectivity. If I can do it without pulling the fan over. Okay. Now, what we're going to do is I'm going to just flick this to make a wave go on it that's up from the wire. Let's watch what happens at the end. Is that end an open circuit or a short? Yeah, it's going to knock the fan over. Is that an open circuit or a closed circuit at the end? Okay, it's tied off, so I would say it's an open circuit. Let's see what happens. Yeah, it's too freaking fast. Let me loosen it up so it's a little slower. Dang, a little too loose. Yeah. You see, and see now how it's just bouncing all over the place? Dave's like, what the heck is going on here? Okay, here we go again.
That's what you engineers do. I was wondering how that
Yeah. Now, did you see it go down and back, and now it's just kind of wobbling around? Watch it again. There, that got it pretty well. Right. So see, and you notice it flips and becomes negative at the other end, right?
Oh, jeez.
Okay, watch. If you can see it, it should be above the wire on the way down and below the wire on the way back.
Anybody feel the need to go hold the fan?
Yeah, I'm trying not to pull it too hard. Okay, but see how it reflects off the traveling wave reflects off the end of the thing. That's what we're talking about with reflectivity. If it's held fixed like that, it bounces off the end and comes back underneath the wire. So that's a negative row. If I attached this like to a ring that could slide up and down a bar smoothly, it would come back on the same side, so that's a positive reflection. So that's all we're talking about here, is we're saying that we want all the energy to reach the fan, or the load over there, and we're bouncing part of it back when we mismatch the impedance. Now, if I had another wire attached to that, what would happen that was the same kind of wire once it reached that spot? Well, let's say that was two wires that were just attached in the middle, right? It just keeps on going. And same thing, if the load matches the wire, if the impedance of the load matches a characteristic impedance, it looks like an infinitely long wire to the voltage, so it just keeps going into the load and doesn't reflect off. Yeah?
Why is it bad whenever there's a mismatch? Why isn't it like as long as the receiving end isn't greater than the transmission characteristic impedance? Why is it whenever there's a mismatch?
Because whenever there's a mismatch, I mean, look at anytime there's a mismatch, we're going to get a reflection. If you look at the equation here, regardless of hold on. The reflection here is ZL minus Z0 over ZL plus Z0, right? So if there's a match, if the load impedance matches rho V equals ZL minus Z0 over ZL plus Z0, if those are the same, it equals 0 over ZL plus Z0 equals 0, right? Let's say that the load impedance is less. Then let's say this, for example, is 1 and Z0 is 2. We're going to have 1 minus 2 over 1 plus 2. So we're going to get negative 1/3. Its amplitude is going to be flipped upside down, but we're still getting 1/3 of the voltage reflected back. And since power is proportional to voltage squared, what's 1/3 squared? Right, so we're losing 1/9 of our power. What if this was bigger? The load impedance was bigger. Say it was 4. We'd have 4 minus 2 over 4 plus 2 equals 2/6, which equals positive 1/3. So 1/3 of our voltage is getting reflected now, which again, regardless of which way is bigger, means we're losing 1/9 of our power, right? Does that make sense to everybody?
Why is it squared again?
Because power is proportional to voltage squared. Right? Remember, it's V squared over R, but we always just
The R is not.
yeah, the R's not. The R's a constant, so we ignore it. Does that kind of make more sense to everybody? What's going on here? Anytime you have a mismatch, it causes you to lose power, and worse than that. Well, does this happen in fiber? Yeah, sure. If you have a mismatch in the optical properties of the line, or even just an inclusion or a crack or anything like that, you get reflections. But the difference there is, in an optical system, optical frequencies are very directional. They act more like a particle zooming along, right? So a particle going backwards reaches the source again, and the source doesn't have anything that detects it, so it just gets absorbed at the source. It doesn't keep bouncing back and forth. But in copper, when we reverse, if we have a reflected wave, it's just going to add on to the incoming wave, and so that creates noise and distorts the wave. Does that make sense, everybody? Okay.
But that's it. So, yeah, I mean, I remember we started this just talking about copper, but this is only relevant for copper.
This is only relevant for copper. Now, there's a similar thing, very similar for fiber. Fiber needs to be matched, but the results are slightly different. Yeah, Major Arbor.
I was just thinking through it. Never mind.
What's that? You were.
I was just thinking through it.
Oh, okay.
If it was the reflected wave was coming back,
Uh-huh.
we said it degraded, but at what point will it just completely be back to the natural source?
That's a good question, because yeah, it's going to attenuate going back that way and then attenuate. But it can bounce back and forth a couple times before it's completely gone, so it causes problems. Okay, so let's look at a quick way to do this. Other thing to be important here is the impedance at any point along the line is this. The reason that's important is when you're trying to deal with antennas and things and you have a certain length cable, well, we'll talk a lot more about this when we talk about antennas, but if you have a certain length cable that's not a set number of wavelengths away, then you're going to have mismatches. But we'll talk more about that a little bit later. Okay, so
Just a question. Would the
Yeah.
mismatched wavelengths, would that damage the equipment or just not give you good?
just not give you good. In general, it won't damage the equipment. It just, you won't get all the power that you want to, and that's a bad thing. I mean, why is that a bad thing? We're like, okay, so we're getting a little less power.
When you get back to that signal noise thing,
Yeah, once we get back to our signal and noise thing, the noise is going to stay the same. Actually, noise is going to increase because now we've got this extra signal going the wrong way that basically we then have to treat as noise. And if that, so we've got more noise and less signal power, our signal to noise ratio goes down, which if we're close already, then we might not be able to receive the signal. And even if we aren't close, we saw that, remember, channel capacity is bandwidth, log 2 of bandwidth times 1 plus the signal to noise ratio. So anytime we lower our signal to noise ratio, we're actually lowering our channel capacity as to how many bits per second can go through it. That's the main reason why, like 802.11n, how many megabits per second should you get from that, theoretically? 54, right? Okay. But as you move farther away, you get less and less and less and less. That's entirely due to lower signal-to-noise ratio. As you move farther away, your signal's getting lower, right? So signal-to-noise ratio is important not just because it's a threshold that we can't receive it below that, but also because it changes our bit error rates, it changes our channel capacity. All of those kind of things depend entirely on signal-to-noise ratio. So anytime we see something that's causing us to lose signal power, that's a bad thing. Does that make sense? Okay, let's look at Smith charts, because everybody loves Smith charts.
Oh, yeah.
And we'd like to thank Captain Smith for doing them for us.
Thanks, girl.
It may have been a collaboration between the Captains Smith, but I don't know.
Phoenix axis up to
Oh, so you did the bendy part. She did the part that's understandable, and you did the part that's annoying. Okay, now here's how a Smith chart works. And this, by the way, is a very simplified Smith chart. If you look at the one that I know that's a good one that you can download as a PDF is the Black Magic made one. So here's the complete Smith chart. Black Magic design. Well, see, now everybody's going to understand this a lot better, right? Okay, so here is. It's hard to get it to fit on the screen and still be readable. Yeah, some of the numbers are upside down.
That's how Stargate works. I've seen it.
Yeah. Where do you think this came? This is obviously alien technology. Okay, here's the way the Smith chart works. You notice along the outside here it says wavelengths toward generator. Okay, so this goes 0. Whoops, I shouldn't be selecting that. 0.3, 4, 5, 6, 7, 8, 17, 18, 19, 0.2, 0.21, 22, 23, 24. Look at that, 0.25 right here. So that's in wavelengths. So going halfway around the Smith chart gets us how far away from the load and towards the generator. Well, quarter wavelength, right? 0.25 of a wavelength. And then you'll notice it keeps on going. 0.26, 0.27, 0.28, and so forth. Up here, 0.48, 49, and we get back here. So one complete circle around the Smith chart is how many wavelengths away from the load? Half a wavelength, right? And then everything just repeats. So, okay, so that's the first thing is recognize that that's wavelengths away from the load. Now, along this center, let me see if I can draw on this. Oh, I can. Good. Along the center axis here, you notice it goes 0.1, 0.2, 0.3, 0.4, 0.5, up to 1 is right in the middle.
Okay, I'll be drawing. Don't see it.
Oh, yeah, I wasn't drawing anything yet.
Oh.
But, yeah, okay, 0.1, 0.2, 0.3, up to right in the middle is a 1, right? Okay, this is the fraction ZL over Z naught. So if it's matched, what's ZL over Z naught? Well, ZL, yeah, it should be 1 exactly, right? ZL over Z naught would be 1. So if we're matched, we're right there in the middle of the Smith chart. Okay, in general, let's say that ZL was half of Z naught. It would be right here, right? Don't know why it keeps popping up those little things. There we go. Right. Stop that. Okay. That little, sorry, it's not drawn very big. Okay, right there. There we go. So at 0.5. So that's just our ZL over Z naught. It goes to 1 in the center, and then logarithmically up to, you notice over here we've got 10, 20, 50, well, what's the end of that, would you imagine? Infinity, right? So, yeah, but anything above 50, they don't usually draw it. Okay, so this is just ZL over Z naught from 0 to infinity is along the center axis. Okay. Now, then the other thing that's around the edge here is going to be this. See this line here? It says inductive reactance component. So this is 0.1, this is J.1, J.2, J.3. And along the middle here, it says resistance component. So this is the real resistance component. So if I drew a dot right here, what would be the impedance of that dot? Let me erase this stuff.
Yeah, ZL over Z naught is 0.2.
Right?
The inductive reactance is J.
0.2. Right, so it would be, this is all just over Z naught. It would be 0.2 plus J.2 over, and everything's just over Z naught.
He said that all those, the 0.1, 2, 3 is actually J.1.
Right. How about right here?
So is that J.2 over Z naught is what that's supposed to be? Or
That would
that's how
be,
you
yeah,
solved it?
0.2 plus J.2. So we go down here to get the real part, and we follow this line up to get the imaginary part.
Okay.
And so this point is 0.2 plus J.2. But then everything on the Smith chart is relative to Z naught. So everything just think of as over Z naught at the end.
So that's what I would write as my answer? So you just put
Yeah, so if I said what is Z of X? Z of X, and let's, if this was a Cat5 cable, I would say it's 0.2 plus J 0.2. Wow, that really is not writing very well over there by the edge. Over 100. Good grief. Yeah, ohms.
Oh man, that just looks like
Wow. That
delta dot.
I know. That, yeah, it's too with the thing recording. It's too slow to keep up with the ink. Yeah, there you go.
We do it left and up or down.
Right. So up is positive, down is negative. How about this point right here, down in the lower right there?
Alright, it's 2
2.0.
and 3. So 2 plus 3J.
Okay, so, close. This would be 2 minus J4.
Oh, I thought you were pointing up there.
Oh, okay. Sorry. I was, okay, this one up here would be, yeah, this one is 2 plus J3, right? And then this one down here would be 2 minus J4. Okay, so you see how the graph itself works? All right, how about let's pick some I can't pick any random point because I can't get beyond the edge. How about right here?
Are you top, bottom, left, right? Where are we?
Yeah, because it's got all the stuff.
Okay, we're kind of center right. That big blob right there.
4.5. I'd say 3.4.
Okay, yep.
Because it's inverse of 2, 2, 4, 6, 8.
Yep, 2, 4, 6, 8, 10.
And
So
then I can't see where
3.4.
it's going to.
10.
Oh crap! I did. Okay, and then
Is it 1?
plus J.
Oh, it's 1. They've got
It is going to be 1. Yeah, so there's the 1 right there.
1J.
Plus 1J. Yeah. So 3.5 plus 1J. Is this kind of starting to make sense, how you read these things?
You said 3.5?
It's 3.4.
3.4, excuse me, sorry, I was... Okay, now, here's how it... Let me now show you how you use this. Okay, so what you do, the very first thing you do is draw a dot at the spot where, so for example, this is my ZL equals 1/2 Z naught. So I draw a dot at 0.5. Then I break out my trusty compass and draw a circle around the middle there. So yeah, everybody's going to Target tonight, right? Get a compass. No.
I'm sure.
Steal one from your kids. No.
Online.
Okay, you don't actually need a compass. Easy way to do this is just mark it on a piece of paper, turn the piece of paper around, make a couple dots. Anyway, you're just drawing a circle, right? Okay, where the circle hits the x-axis over here on the right is your viswar. So I already know now my viswar is 2.
What's the viswar again?
Voltage standing wave ratio. That tells us how much reflectivity is going on. We want it to be 1, right? Okay, then the next thing is I can find z of x at any distance from the load. Like if I want to find it at 0.15 wavelengths away from the load, I just draw a line straight out to 0.15 here. And where that crosses my circle, I see that the impedance at that point is 1 plus j, I don't know, 0.7 maybe. I'm going to follow this out to the edge. It's not drawn on there, but since that's 0.6, this is probably about 0.7. So I know that z at 0.15 and t equals 1 plus j 0.7.
Yeah, one more, please.
Okay, actually, let me switch slides really quick because the slides have drawn on here. Okay, so x-axis is resistance, y-axis is the distance from the load, goes around the outside, and everything on here is normalized. That once around is a half a wavelength. Reflection is indicated by circles of constant viswar. So let's do some example points. So far point on the far left labeled 0 is the chart's origin, right over here. That's the origin. Point labeled D, where's D? Oh. D right here in the center is Z over R naught equals 1 plus J0, which is where Z equals R naught, so that's where we want to be. That means it's matched. So we want to always try and get to the center. Now, the arc labeled A right here, all points along this arc, we would have J, so like this would be, Q would be 0.2 plus J 0.5, right? A would be, I don't know, 0.35 plus J 0.5. This point over here would be 2 plus J 0.5, and so forth. Okay, so that's how you read points off of it.
What did you say A was again?
A is just I'm just showing that this arc, it's along the line where J equals 0.5. Okay, now let's do a couple other examples. Okay, point P lies on arc A. It lies on the circumference, so if we follow that down to the x-axis, we get 0. So point P is 0 plus J 0.5, right? Point Q is 0.2 plus J 0.5, and so forth. We already talked about those. J and K over here. J, what's its impedance? Well, we follow this arc down. 1 plus J 1.5. Yep. How about K?
That's 2 minus negative 1.
Yep. 2 minus 1J. Yep. Okay, see, it seems like you guys have got this pretty well. Okay, now let's look at, so every point around the outside is purely reactive, because it's always 0 plus J something, right? And then here's, yeah, that's just the ones we already looked at. So let's look at an example. Let's say that ZL equals 0.5 Z naught. You get this a lot, like if you split, for example, if you plug one of those little headphone splitters into your iPod and listen to 2 sets of headphones at once, you're actually doing this. You're making the load equal 0.5 Z naught, right? Because you're putting 2 sets of headphones in parallel, so the total load impedance is going to be 1/2 of the characteristic impedance. So this is like a Y joint does that. And now we want to look at a point X, which is 1/8 of a wavelength away from the load. So we can use the equations. We find out that rho V equals ZL minus Z naught over ZL plus Z naught, and we get, look at that, minus 1/3, which is what we just did on the board earlier. Because we get ZL is 0.5 Z naught, so 1/2 minus 1 over 1/2 plus 1 gives us minus 1/3. Viswar is 1 plus the absolute value of rho V over 1 minus the absolute value of rho V, which gives us 4/3 over 2/3, so Viswar is 2. And then we can find, at a point lambda 8th away from the load, we can find that beta x equals 2 pi over lambda times x, which is lambda over 8, gives us pi over 4, which is 45 degrees. So tangent of beta x equals 1. And then we can plug that into this equation, and we get ZL plus JZ naught, tangent of beta 1 is beta x is just 1. So ZL plus JZ naught over ZL Z naught plus JZL. JZ? What? No. And we get 0.5 plus J over 1 plus 0.5J equals 0.5 plus J times 1 minus 0.5J over 1.25, which equals 1 plus 0.75J over 1.25. Equals, finally, 0.8 plus 0.6J. And that's just plugging it into this equation, right? Now let's look at doing that on a Smith chart. So we got Viswar equals 2 and Z of x equals 0.8 plus 0.6J. Let's do the same thing here. RL is 0.5, so we make a dot here at M, right? Then we draw this circle to get the Viswar, where the circle intersects the x-axis over here on the right is at 2, so Viswar equals 2. So far it's been a little easier than how we solved it the other place, right? Lambda over 2 is once around the circle, so lambda over 8 is 1/4 of the way around the circle. So we're going to draw a line from the center to 1/4 of the way around the circle, straight up and down, which intersects the circle at point N. Everybody see that? Okay, what we're doing at this point is, okay, remember going this way means we're increasing our distance from the load, right? So what is 1/8? 1/8 is 0.125, right? So we just go around here till we see 0.125. Here's 0.1 and 0.15. So 0.125, whoops, 0.125 is right there, right? We're going to draw a line from D straight up to 0.125, and it's going to cross this line at point N. It's going to cross our circle. Now we just need to look at point N. We follow this curve down to the x-axis, and it intersects, I would say, at about point 8, wouldn't you?
Sure.
And we follow it up here, and it intersects at 0.58. So we get that z of x equals 0.8 plus j 0.58, which amazingly is pretty much the same thing we got with the math, although we rounded it off to 0.6 when we did the math, right? 0.8 plus 0.6j. We get that same thing there at point N. R(n) equals 0.8, xn equals 0.6. And now the absolute value of that equals 2. So minus z equals 2 plus j0. Ta-da. What we're saying here is z at a quarter wavelength away from the load. See, now we can do it. Yeah, z of lambda over 4 is just straight out there. So that's 2 plus j0, right? What about lambda at 3/8 of the way away from the load? It's going to be along a line straight down. So right here, which is going to be 0.8 minus j 0.6. Now I can just do any distance away from the load. I just draw a line out to the edge, and where it intersects my circle, that gives me the impedance at that point. It was like, maybe if I'm quiet, he'll stop talking. Punch him. All right. Well, there is a homework problem that you can look at that has to do with this. Other than that, we will talk a little bit more about why we're interested in this. But main idea, takeaway from transmission lines is that we can find the impedance at any point along the line, and that we get the most power if we can match the load to the characteristic impedance of the line. Those are the main points. Then this stuff gives us some of the details. Have a good lunch. We'll work on homework after, I guess. Tomorrow, let me take a look at, oh yeah, tomorrow is Friday.
I'm not trying to push it out, but I know if we wait until we actually finish this whole sheet and just turn it all in, and I'm not trying to drag it out.
But yeah, let's push it.
No,
and
fair
also,
enough.
I mean, some people that just finished the math test.
Some people that just finished the math test. I'll tell you what. Let's have the whole sheet. We'll just have it due Monday.
So tomorrow we're gonna actually finish this out, so we'll be able to do the
But
whole.
I will. Yeah, tomorrow we can
Okay.
do the whole thing
Okay.
for sure.
All right. That's good.
And then yeah, we'll have it
What do
due
you want?
Monday. And since we just the electronics thing has been just kind of hanging out because people were doing the math test. How about if that's the electronics one we'll have due tomorrow so that I can
Okay.
grade it over the
First
weekend.
Two little whatever. Okay.
Yeah, those first two little ones from basic electronics are due tomorrow, and then
This whole thing is
this
due
whole thing is
Monday.
due Monday. Sweet.
Is that a movie?
Yeah, we gotta finish it. Gotta finish it.
Oh, you're gonna finish the
Yeah.
Wars?
Let me stop this thing from
So much
recording.
burning.